Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is coordination compounds, ligands, crystal field theory and nomenclature. Coordination compounds are an important topic in chemistry, especially for students preparing for competitive exams like NEET and JEE. These compounds exhibit unique properties and play a crucial role in various chemical and biological processes. Understanding their structure, bonding, and nomenclature is essential for mastering this topic. To begin with, coordination compounds consist of a central metal atom or ion that is bonded to molecules or ions known as ligands. These ligands donate electron pairs to the central metal, forming coordinate bonds. The number of ligands attached to the central metal is called the coordination number, which determines the shape and stability of the compound. Different ligands have varying abilities to donate electron pairs, affecting the overall properties of the complex. Ligands can be classified based on their denticity, which refers to the number of donor atoms they have. Monodentate ligands have a single donor atom, meaning they form only one coordinate bond with the metal center. Common examples include water, ammonia, and chloride ions. Bidentate ligands, on the other hand, have two donor atoms that can simultaneously bind to the metal. Ethylenediamine is a well-known bidentate ligand. There are also polydentate ligands, which have multiple donor atoms capable of forming several bonds with the central metal ion. EDTA is an example of a hexadentate ligand, meaning it can bind at 6 positions, making it highly effective in complex formation. Now, let's explore crystal field theory, which explains the bonding and properties of coordination compounds. According to this theory, when ligands approach a central metal ion, they interact with its d orbitals, leading to the splitting of these orbitals into two energy levels. The way this splitting occurs depends on the geometry of the complex. In an octahedral field, for instance, the d orbitals split into two sets, one with higher energy and one with lower energy. The difference in energy between these two sets is known as the crystal field splitting energy. This energy gap determines the color and magnetic properties of the coordination compound. Strong field ligands, such as cyanide, cause a larger splitting, often leading to low-spin complexes, whereas weak field ligands, like halide ions, result in smaller splitting and high-spin complexes. The coordination number of a metal ion in a complex is determined by the number of ligand donor atoms directly bonded to it. This number varies depending on the metal ion and the nature of the ligands. Common coordination numbers include 4 and 6, which correspond to tetrahedral, square planar, and octahedral geometries. The geometry of a coordination complex influences its chemical behavior and properties. One of the most important theories used to explain the bonding and properties of coordination compounds is the crystal field theory. This theory describes how the d orbitals of the central metal ion interact with ligands, leading to energy differences among these orbitals. When ligands approach the central metal ion, they create an electrostatic field that splits the degenerate d orbitals into two or more energy levels. The extent of this splitting depends on the nature of the ligands and the arrangement around the metal ion. In octahedral complexes, the d orbitals split into two sets, the higher energy Ag orbitals and the lower energy T2G orbitals. The energy difference between these orbitals is known as the crystal field splitting energy. Strong field ligands, such as cyanide and carbon monoxide, cause a large splitting, leading to low-spin configurations. Weak field ligands, like chloride and fluoride, result in smaller splitting and high-spin configurations. The electronic arrangement influences properties like color, magnetic behavior, and stability. For tetrahedral and square planar complexes, the crystal field splitting pattern is different. In tetrahedral complexes, the splitting is smaller, and the T2 orbitals are higher in energy than the E orbitals. As a result, most tetrahedral complexes are high-spin in nature. Square planar complexes, commonly observed in D8 metal ions like platinum and nickel, have a unique splitting pattern where electrons tend to pair up in lower energy orbitals, making many of them diamagnetic. One of the most fascinating aspects of coordination chemistry is the nomenclature of these compounds. The naming system follows specific rules to ensure clarity and uniformity. The name of a coordination compound begins with the ligands listed in alphabetical order, followed by the name of the central metal with its oxidation state indicated in Roman numerals. Anionic ligands are given names ending in O, such as chloro for Cl and cyano for Cn-. Neutral ligands generally retain their common names, like water being called aqua and ammonia as amine. If the complex is an anionic species, the metal's name ends with ate. For example, if cobalt is the central metal in an anionic complex, it would be named as cobaltate. Understanding these naming conventions is essential for correctly identifying and communicating information about coordination compounds. Coordination compounds play a significant role in various fields, including medicine, industry, and biological systems. Hemoglobin, the oxygen-carrying protein in our blood, is a classic example of a coordination complex where iron is coordinated with nitrogen atoms of a porphyrin ring. In industry, coordination compounds are widely used as catalysts, in electroplating, and in the production of dyes and pigments. Their diverse applications make them an indispensable area of study in chemistry. Mastering coordination compounds requires a strong grasp of ligand classification, crystal field theory, and systematic nomenclature. By understanding these concepts, students can tackle complex problems and enhance their problem-solving skills in chemistry. Keep practicing and revising these topics to build a solid foundation for exams and beyond. Thank you. We hope this video has helped you gain a clearer understanding of hydrogen and its compounds, especially the fascinating role of heavy water and isotopes. If you found this video helpful, make sure to like, share, and subscribe to AskPrep for more in-depth chemistry lessons. Keep studying, stay curious, and good luck with your exams.